Hello and welcome to this lesson in our study of linear algebra. This lesson we talk about reduction to a canonical form. So when you have a quadratic form, when you have a quadratic form, x equals to q equals to x transpose ax. If A is real symmetric, then A has orthogonal basis of n vectors. Okay, so the canonical form, to transform a quadratic form to a canonical form, we go through some steps. Then we apply the principal axis theorem. Principal axis theorem states that when you have n eigenvalues, then the canonical form is given by this. Okay, so before we solve example, let's study the procedures that would help us to transform quadratic form into canonical forms. Okay, so here are the procedures for reducing quadratic form to canonical form. So when you have a quadratic form, q equals to q of x equals to x transpose ax. So this is the first step. You find the real symmetric matrix A, okay, from the quadratic form. Then you find the eigenvalues of A. You find the corresponding eigenvectors of A. You verify that the eigenvectors are orthogonal. You construct the normalized modal matrix such that the columns of the modal matrix P are the normalized eigenvectors of matrix A. Then we diagonalize the matrix D, or we say D equals to P transpose AP. Then finding the canonical form, we set x equals to Py. Okay, so you see we know that our q of x equals to x transpose ax. So when we set x equals to Py, we replace x by Py. When you do that, we get this, and this is the same as that, but we know that P transpose AP is what? D from here. That's from the C step. So we can rewrite q of x as y transpose dy. So we let y be any vector of finite dimension. So you have y equals to y1 up to yn. We have D, that's the diagonalized matrix, that's lambda 1 0 0. The columns of D are the eigenvalues of symmetric matrix A. Then we see our q of x is y transpose dx dy. Y transpose dy. So this is the transpose of y. This is d and this is y. Okay, so when you solve this, you get this. So we have to note the following. We have some conic sections. We have parabola, hyperbola, ellipse. We'll talk about circles. Circles especially are conical section. So this equation of a circle, this equation of an ellipse, hyperbola, then point of pair of straight lines. Okay, so now let's go back to the slides and continue. So here is an example. Okay, we have an example here. We have to find out what type of conic section the following quadratic form represents and transform it to the principal axis. So we have this quadratic form. So we can write q of x quadratic form as x transpose ax, where 17, our matrix A is what? Given by this. It is generated from this. So we get 17, negative 15, negative 15 is 17. So we find the eigenvalues of this matrix, that will be 17 minus lambda minus 15 minus 15, 17 minus lambda, then equal to 0. Okay, so when you do that, you get our lambda 1 to be 2 and our lambda 2 to be 32. Okay, then from the principal axis theorem, we have lambda 1 y1 squared plus lambda 2 y2 squared equals to q of x. Okay, so our lambda 1 is 2, our lambda 2 is 32, so we have 2y1 squared plus 32y2 squared equals to q of x, which is 128. So we get this. We can divide through by 128, and when we do that, we get this. Okay, so this is an equation of an ellipse. Okay, then we transform it to the principal axis. If we want to do that, we find the eigenvectors of A. So we find the normalized eigenvectors of A. Okay, so the corresponding eigenvector of 2 is given by this. That's 1 over root 2, 1 over root 2. Then the eigenvector of 32 is also given by that. So you can use it to construct your normalized modal matrix. So that's what we have here. Okay, so we set x equals to xy. Okay, where x is the modal matrix, so that the columns of x are the normalized eigenvectors of matrix A. So we have this matrix times the vector y. So when you simplify this, we get x1 equals to y1 over root 2 minus y2 over root 2. Then x equals to y1 over root 2 plus y2 over root 2. Okay. Now let's look at another example. Let's consider another example. So you can pause your video and try your hand on this question. Yeah. So we have to find out what kind of conic section are. We have this quadratic form, x squared minus 12xy plus y squared equals to 70, and we have to transform it into the principal axis. So we write this as q of x as x transpose ax. Okay, x transpose ax. Okay, so this q of xy. Okay, q of xy. Okay, let's use q of x is fine. Okay, so we write it this as this. Okay, so our a is given by this. That's 1 negative 6 negative 6 1. Then we find the eigenvalues of a. Okay, that's we use this formula, the determinant of, you see, we have a, we have av equals to lambda v. This is the same as av minus lambda v equals to 0. And factorize v out, we have a minus lambda I, okay, equals to 0. Then when you have this, either v equals to 0 or a minus lambda I is equal to 0. Okay, but if v is equal to 0, it means we get trivial solution. So it means that v is not equal to 0, and automatically lambda a minus lambda I equals to 0. And since a minus lambda I is equal to 0, it means that the determinant is also equals to 0. Okay, so that's why we obtained how we generated this formula. Okay, so we subtract lambda from the diagonal element, so we have 1 minus lambda negative 6 negative 6, 1 minus lambda equals to 0. Okay, so when you find a determinant, so that will be 1 minus lambda times 1 minus lambda. That's what we have here. Minus 6 times minus 6, that's 36. So 1 minus lambda squared minus 36 equals to 0. When we expand bracket, we get this minus 36 equals to 0. When we simplify, we get this. And when we can factorize this completely, then we get that. And lambda plus 5 equals to 0, or lambda minus 7 equals to 0. And when we simplify, we get negative 5. And that's negative 5 to be lambda 1 and lambda 2 to be positive 7. Then from the principal axis theorem, our Q of x, so here we have two eigenvalues, so our Q of x will be lambda 1 y1 squared plus lambda 2 y2 squared. So lambda 1 is negative 5, so you have negative 5 1 squared plus 7y2 squared equals to Q of x, while Q of x in the question is given as 70. So we can rewrite this as that, and we can divide through by 70. When we divide through by 70, that will be 7y2 squared over 70. That's so this is supposed to be, so this y2, okay, y2 squared over 10, and this is supposed to be y1 squared over 14 equals to 1, and this is what hyperbola. Okay, so the conic section is hyperbola, and this is the sketch. It's at the origin. Okay, it's at the origin. So we take the square root of 10, so that will be plus or minus 10. So we have plus or minus root of 10, so you have minus root of 10, half root of 10, square root of 14 plus or minus root 14. That's what we have there. So this will be the conic section. The conic section is what this will be. This is the sketch of the conic section. That's hyperbola. So now let's transform it into the principal axis. Okay, to do that, transform it into the principal axis, we find the corresponding eigenvectors of A. Okay, so let's consider each of the eigenvalues. So when you consider lambda 1 to be negative 5, we let v1 to be a1 a2 such that a minus lambda 1I times v1 equals to the 0 vector. So we subtract minus 5 from the diagonal element, but you see, have 1 minus negative 5, which is 1 plus 5. So minus 6, 1 plus 5, a1 a2 equals to this. So when you do that, we get this. Okay, we divide row 1 by 6 and divide row 2 by 6. Okay, so we divide each row by 6. So when you do that, we get this. Also, so after getting this, we use the elementary row operation. That's row 2 given by row 2 plus row 1, and when you simplify, we get this. Okay, so 1 times a1 is given by a1 minus a2 equals to 0. It means that you select a2 be a free vector. Okay, so it is the same as a1 equals to a2, and when you set a2 to be 1, it means a1 is also to 1. Okay, or in short, a1 is equal to the coefficient of a2 and a2 is the coefficient of a1. Okay, so each of them have coefficient 1 1, and therefore a1 is equal to 1, a1 equals to 1, a2 also equals to 1. So our v1, that's the normalized eigenvector, is given by 1 over root 2, 1 over root 2. Okay, Now let's move on to the another one. So when lambda equals to 7, when you have lambda equals to 7, then we let our v2 be b1 b2. Okay, so this is given by we subtract 1 from the diagonal elements. Okay, so that's what we subtract 7 from the diagonal elements. That's 1 minus 7, negative 6, negative 6, then 1 minus 7, b1 b2 equals to 0 0. When we simplify, 1 minus 7 is negative 6. We have negative 6, negative 6, negative 6. So we divide each element in the matrix by negative 6, or better still, we divide each row in the matrix by negative 6. When we do that, we get this. Okay, so now this time around we use the elementary row operation. That's row 2 minus row 1 to reduce the number of rows. Okay, so when you do that, we get this. So that's b1 plus b2 equals to 0, and this is the same as b1 equals to negative b2. Okay, and b1, therefore from here we can say that the b1 is equal to negative 1 and b2 equals to 1. Okay, so v2 is the normalized eigenvector, okay, of v equals to 7. So you can generate our modal matrix so that the columns are the normalized eigenvectors. So this is our P. Okay, so before then, let's verify that the eigenvectors, normalized eigenvectors, are orthogonal. So we have our v1 to be 1 over root of 2, 1 over root of 2, our v2 to be minus 1 over root of 2, 1 over root of 2. So let's find the inner products. So v1 dot v2 is v1 transpose v2. Okay, so we have 1 over root of 2, 1 over root of 2, minus 1 over root of 2, 1 over root of 2. So 1 over root of 2 times minus 1 over root of 2 is minus 1 over 2, plus 1 over root of 2 times 1 over root of 2 is what? 1 over 2. And this gives you what? 0. And therefore, our vectors v1 and v2 are what? Orthogonal. Okay, they are orthogonal. So v1 and v2 are orthogonal. If they are not orthogonal, then you have to use the Gram-Schmidt orthogonalization process to find the corresponding orthogonal set of vectors, or corresponding orthonormal set of vectors. Then you proceed from there to solve the problem. So now transforming it into the principal axis, we set x equals to py. We know a p to be the modal matrix, so we let x to be x1 x2 and y to be y1 y2. Okay, we're using x that's 2 dimension because the matrix A, or the modal matrix P, is what? Also 2 by 2 matrix. So therefore x, this p, this y. So when you multiply this matrix by vector, we get y1 over root 2 minus y2 over root 2. And when you consider the second row, we multiply by vector, that will be y1 over root 2 plus y2 over root 2. But you see, these two vectors are equal. Okay, that's equality of vectors. And therefore, our x1 is this, that's y1 over root 2 minus y2 over root 2. And our x2 is y1 over root 2 plus y2 over root 2. Thanks for watching.